previous speakers. I'm Kevin Lin. I'm a senior researcher at Microsoft, and in this talk, I will provide a brief review of recent advancement in video and 3D generation. Diffusion models have made significant advancements in the recent year, especially for video generation. And we can see in the slides, the result is pretty amazing. The progress have been made from low to high resolution video and extending from the very short, like 4-second clips to 1 minute long videos, where the results also preserve the character identity and maintaining the 3D consistency. So an important takeaway from the SORA research is that researchers found that scaling the video generation model is a very promising path toward building a general purpose simulator for the physical world. So this is the outline for today's share. We will begin by introducing the development of the video diffusion models, and then we will highlight several key observations in the latest video generation research. Next, we will talk about some of the rapid growing topics in this year. First, one important and exciting topic is that how to develop a training efficient models, training efficient approach for building the video diffusion models. And second, we will also talk about the accelerating the video diffusion inference. We will mainly talk about the few step diffusion distillation for the video diffusion model. And finally, we will also cover some of the topics for generating diverse video content creation, such as the long video generation, video editing, and the 3D generation. So one representative task in video generation is the creating video from text, or commonly referred to the text to video, or T2V. So given the input text prompt as shown in the slide, the goal for the video generation is to generate a video that can accurately represent the text description provided. So this text is actually relevant to the previous talk about the text to image generation. One important challenge or the main difference here is that we need to address the coherent and consistent visual element generation across the temporal dimension. So to address the challenge, especially for the temporal dimension, researchers have found that we could inflate the UNet in the image diffusion model to 3D. And this has been shown is a promising approach. So this approach offers several benefits. First of all, we can leverage the well pre-trained text-to-image generation model as the initialization and further continue the training. And secondly, by adding the additional temporal attention layers to the model, we can train both the UNet and the newly introduced parameters, and then the model can effectively model the object motions. So here, this is an example that demonstrates the researchers how they enable the transition from the pre-trained text to image model to the temporal dimension. So we can see that each spatial 2D convolution layers is followed by a temporal 1D convolution layers. And the temporal convolution layers is initialized as an identity function. So given this modification, we further train the model using the text video pairs data to learn the video generation. So this is about the extending the convolution to the temporal dimension. And also, we also attend the temporal attention layers. The temporal attention layers is also applied following the spatial attention layers. So the temporal attention layers are initialized with the temporal zero projection, and then resulting in identity function. So with the inflated U-net, researchers found that we can actually fine-tune the inflated U-net on small and high-quality video data sets and demonstrate in the pioneering research. This fine-tuned model are capable of generating the short video clips with this specific video content. So one important question is that how we can train a video diffusion model for a wider range of visual content. So along this research line, like as shown in the stability AI researchers, they found that if we continue to scale up the training data, like researchers have, like in the stability AI researchers, they have built a system that to curate large amount of video data and transforming the large and noisy video data into a suitable data set for the generated video models. So we can see that by simply scale up the training data, we can directly obtain such good quality improvement. So in addition to the training data, there's another important factor like the model. So model size also plays a crucial role for the performance improvement. Like as shown in the Sora technical reports, the diffusion model can be scaled effectively. So as we can see in this comparison, when given the fixed state and the input prompt, and when training continued, we can see that the sample quality would improve as training computes increase. So now we have talked about like the large video foundation model, and we will next discuss some important findings and highlights two important directions to make video diffusion model more efficient. So one direction is developing the training efficient techniques. So ideally, we wish to have we wish to achieve high performance with small amount of training data and maybe shorter training duration. However, this is still a very difficult and open questions. And recently, there are some of the interesting research like AnimateDiff. They propose to insert the motion modules to a pre-trained personalized text-to-image model. So by training just the motion modules only, the model can learn the motion priors while alleviating the visual quality degradations. So this offers a practical pipeline to directly turning the personalized text-to-image model for animation generation. So we briefly discussed about the training efficient techniques. Another practical topic is accelerating the diffusion sampling process, particularly by reducing the number of sampling steps while maintaining the similar visual quality. So as we can see on the left-hand side, this is the result from the IMU video paper. So typically, they usually require about 200 sampling steps in the inference stage. And it would be nice if we can reduce the sampling steps to maybe 4, 2, or just 1 steps. So as discussed by Zhenyuan in the previous sessions, so the consistency model is a very promising method for faster image generation. So previously introduced a new learning objectives that maps the noisy images at any time steps to any time step of the diffusion process back to their initial states. So although this is great, but it may be difficult to directly apply it to the video generation. So when it comes to video, we need to consider both the spatial and temporal dimensions. This means that we should account for both the motion and appearance consistency. So while there's a large number of high quality and high resolution image data, video data are often of low quality and may contain watermarks. So given this is also a data challenges that make the distillation process difficult. So recently there's a paper called motion consistency model. So the author proposed to distill the motion prior from the text to video teachers, and then they also proposed to improve the frame quality by using additional high quality image data set. So here from this work, we can see that the motion consistency model not only it greatly reduced the number of sampling steps, and also because it can leverage different kind of image data set to improve the frame quality. So in the slides, it shows some of the quality results using different image data sets, like using WebVid video frames only, or using Lion Authentics, or Anime or Realistics, or 3D cartoon style image data sets. And then the method can generate diverse and good quality. So next, we will discuss how we apply the video diffusion model for diverse content creations. We will highlight 3 fundamental challenges in this area. First is about how we generate a long video, or to generate variable durations. And second, the second fundamental challenge is to have the controllability in the video diffusion model. And finally, as we are generating the video, the consistency is always an important challenge. So I would like to highlight, first of all, for the variable video durations generations, one challenge is to generate long video. So to generate the variable video length to enable extremely long video is very difficult. And the recent study have shown some promising progress, like by using a close to fine process. Like as shown in the example, the author proposed to first generate a few frames, like 16 frames, and then given the 60 frames, it continued to generate about 200 frames, and then 3,000 frames. And finally, we have a long video. So here, behind this idea, the author proposed to using this close to fine approach. It is more like to have diffusion over diffusion. So at the core stage, we will have a global diffusion, and then after the global diffusion, we will have local diffusion to generate a detailed frame for each segment. So we talk about, in the previous example, researchers mainly focus on relatively simple scenario like cartoon videos. And another important and very challenging direction is to create rich and diverse video contents. And can we generate such video content like the TikTok videos? So recently, so first of all, researchers have explored this direction. I would like to highlight this one, like generating the human dance videos. So generating human videos is a lot more challenging than creating the cartoon, because it requires accurate body pose and realistic appearance. So recently, like this example, researchers have shown promising progress in human dance generation, and with the ability to compose different subjects in the same dance pose. And similarly, we can also compose the different posts with the same subject. So the core idea in this work is that we could leverage the control net and the U net together, and then combine them together for this kind of video human dance generation. So the author proposed to disentangle the control from the three conditions, including input frame, the background, and the pose. So given this, the method can enable arbitrary compositionality for human subject, background, and dance moves. So in addition to the human dancing videos, recently researchers also show that we could synthesize a series of diverse 3D scenes starting from an arbitrary location or specified by a single image or just a language description. So in this work, the author proposed to leverage large language model to generate scene descriptions, and then we could employ the text-driven visual scene generation, and then we could use the all-painting text guided all-painting to generate the complete scene. So basically, this shows a promising signal that we could generate a long sequence of diverse and connected 3D scenes by leveraging existing all-painting and existing scene generation approach.
Recent studies showed great advancements using multi-view diffusion model. For example, CAT 3D used a multi-view latent diffusion model to generate novel views of the scene. This model can be conditioned on any number of the views and is trained to produce multiple consistent novel images of the scene at a specific target viewpoint. In the proposed method, their model architecture is similar to the video diffusion models, but with camera pose embeddings for each image instead of the time embeddings. The generated views are passed into a robust 3D reconstruction pipeline to generate the 3D representation. So far, we have discussed topics such as coherent generations as discussed in the long video generation example. We also discussed the realistic content generation such as adding the human pose as a condition for human dance generation. Also, we highlight several recent advancements in 3D consistency generations. These are the important milestones toward building a world simulator. As shown in the video results, Sora can generate videos with dynamic camera motion. As the camera rotates, we see that people and scene elements can move consistently in the 3D space. We also see that Sora generates minute-long videos while preserving character identity, even if there is occlusion or the subject leaves the frames. While Sora has shown very promising results, there remains a lot of opportunity and challenges. The first challenge is accurately modeling the physical and digital world when building the world simulator. State-of-the-art models still have room for improvement. They may struggle to simulate the physics of complex scenes and may not fully comprehend specific instances of cause and effect, as the models are primarily trained on video text data. We may need new training approaches to learn abstract concepts that are difficult to describe in language. The second challenge is evaluation. We need new evaluation benchmarks and metrics to assess the quality of the video generation models. Finally, safety and privacy are crucial topics. It would be helpful to build tools to detect misleading video content. We should engage artists and general users in the world to understand their concerns and identify their positive and negative use cases for this new technology. We recently introduced a new evaluation benchmark called MM-Word. This benchmark aims to evaluate multiple capabilities of the word model in videos, such as feature prediction, attribute or temporal understanding, and counterfactual thinking ability. So, what is a word model exactly? According to the researchers, a word model refers to our ability to build internal representations of the word, predict and simulate future events within these internal representations. By predicting the future, we can reason and plan better. Given these notions, it offers a great opportunity for us to rethink the design and development of video diffusion models. I would like to summarize today's talk. First, we discussed innovative work in video diffusion, such as incorporating temporal attention into existing UNet architectures for motion modeling. We further highlight the key findings in the latest video generation foundation models. For instance, we highlighted how scaling data and model size significantly improve the performance. We covered techniques to reduce training costs, such as training motion modules, as demonstrated in Animate Diff. We discussed challenges and research efforts aimed to speed up video generation. We briefly touched on topics like long video generation, conditional video generation, and 3D generation. Finally, I would like to thank our outstanding interns for supporting this tutorial. Here is a list of online resources, including YouTube and blog tutorial on diffusion models. You may find this helpful. Thank you.